Good afternoon. Any questions? Questions on the homework? Yes. What's that?
I'm asking the obvious question.
Whether you can succeed without studying. No. Yeah.
I don't have any good questions right now, only bad ones.
All right, hearing no good questions, we'll move on. So today I want to talk about types. First of all, what's a type? You know types intuitively. Int is a type, right? What does that mean? That means that there's some values that have that type, and for int, those values would be all those 32-bit quantities between integer.min value and integer.max value. So that's all the values of this type. And then there's things that you can do with integers. You can add and subtract and compare them and so on. And so in general, that's what a type is. It's a set of values together with a set of permitted operations on these values. And double is a different types. The values are different, and the operations are a little different. Like you can take a square root of a double, but you can't take a square root of an int without first converting it to a double, of course. An array of int is a different type. Like you can't take two array of ints and add them, at least not in Java. Maybe in Fortran you can, but in Java you can't. So a type has values and operations that are permitted on that. So why do we have types? You don't really need types. You could erase all of the type declarations from your programs. Would be less typing, no pun intended. And then, your program could probably still be translated. And to some degree, you know that because there's some languages where you don't really ascribe types to variables and function parameters and so on. Like when you program in JavaScript, you don't say this variable needs to hold a particular type. So different languages deal with types differently. When you program in assembly, you don't really deal with any types, right? You just move these bit patterns across and run processor operations, and there's no expression that this particular memory location needs to hold particular types and so on. But generally, programmers like types. A language that has no typing at all, like SL1, is not something that would win the hearts and minds of programmers, because there are certain things that you could not do if you didn't have access to types. Like a very obvious thing is IDE help. You're coding away, and you're having a variable name, and you want to now call a method on that variable. You type dot, and what is the very next thing that everyone does? You hit Control space, right? Because you want the IDE to tell you what are the various operations on there so that you can pick the right one. Maybe you type the first letter of it. But most people rely on auto-completion by the IDE, and that's driven by types. And you can see that when you code in JavaScript. And the JavaScript IDEs have a tougher time with doing that kind of auto-completion. In Java or in Scala, if you have a variable that's declared as a string, and now you type whatever that variable was, dot to, then it'll do to lowercase, to uppercase, and so on. In JavaScript, how does the IDE know that that variable contains a string? Some IDEs will actually try to follow along how it was initialized, and will work on the assumption that most JavaScript programmers implicitly don't respect types, and they would not put an object into a variable that previously contained a string. On the other hand, some JavaScript programmers don't do that. They just call their variables A, B, C, and D, and they just put in whatever. At any rate, the IDE has a tougher time if it does not have the guidance by the type system. Another thing is code generation. In Java, when you have a call such as s dot to lowercase, then the Java compiler can produce very precise code because it knows that s has to be a string, so it can call the method directly. In JavaScript, when you put s dot to lowercase in the program, the compiler has to make a type inquiry and say, is S really a string? And if so, call to lowercase. Or S might be something, some other thing that happens to have it to lowercase, so it has to dynamically make that determination. And that's, of course, much slower than directly calling a particular method. So having types can yield to better code generation because there's fewer decisions, or maybe no decision, that have to be made at runtime. Another reason that programmers generally like types is that they can give you earlier error diagnostics. If the compiler tells you that you have made a type error and you need to fix it, that's usually a very speedy process. You get wiggly underlines, you just say, oh, I was a knucklehead, you fix it, and then you move on. Whereas if the type error is only detected at runtime, you would get an exception, then you have to go and find out, okay, what was the line of code, what was the execution history, and it's usually more tedious to recover from that kind of type error than if it just happened at compile time. Or if the runtime system didn't find the type error, and the program just kind of meandered along and caused a seemingly unrelated error much later, then the debugging gets really nasty. So people who program in very low-level languages such as assembly or C will sometimes have those kinds of errors, and they would really wish that there had been a runtime exception instead of just some silent data corruption. So types are these helpful things. And so today I want to talk a bit about types and also talk about what makes types difficult, because they start really simple and then they get surprisingly complex kind of quickly. So let's look at good old Java. In Java we have a fairly simple type system. There are 8 primitive types. These special cases, in, short, long, byte, car, float, double, and Boolean, that are there for efficiency because in 1996 the designers of the virtual machine did not know how to efficiently handle those things if they had been implemented as objects. And the virtual machine at the time was very primitive. We've ever since regretted that decision, but there it is. Every type that's not a primitive type in Java is a reference type. We can declare 3 different kind of reference types: classes, interfaces, and arrays. You could argue that arrays are in a way classes, but we'll keep them as separate types here. So those are the 3 kinds of types that you can form in Java. Notice that arrays are type constructors. You can form an array of any other valid type. These are the kinds of types that you can have for variables. There's somewhat different types when you look at values, because you cannot have a value of an interface type. Every value that you ever encounter in a Java program has to be an actual object of a class. On the other hand, you can have a value that's not listed here, namely the value null. You could never declare that a variable must contain null or can't contain null. So the system for types is a little, on variables versus types for values is slightly different. Now notice the absence, some of the things that you do not have in Java. Ever since Java 8, we have lambda expressions. Right? You've seen those lambda expressions. But in Java, a lambda expression is not a type. There's no type that you could write down in the Java programming language that says, initialize this variable with a lambda expression. All you can do is you can say, the type of this variable is a functional interface. And then yes, you can take a lambda expression and on the right-hand side, and it gets instantly converted into an object of a class that implements the functional interface. By itself, that lambda expression has no type. There's nothing that you can write down in the Java language for that. Now what about Scala? So in Scala, we have a large number of additional types many of which we're not introducing in this course at all, but there are a couple that you have seen that don't have equivalents in Java. In Scala, you have these tuple types, such as the tuple of string comma int. That's a type. There are certain operations that you can do on a tuple type, namely do the _1, the _2, or the matching with match expressions. And there are function types. So here I have a function type, the functions that consume two strings and return an integer. So the tuple and function types are things that you have in Scala. Like I said, in Java there are no function types. Now you might say, why didn't Java do what Scala did? Why didn't Java give us a bunch of function types for those lambda expressions? And the designers of Java briefly considered that, because it would have made the language in a way simpler. One wouldn't have had to have these funky functional interfaces. You could have had true function types. And there's a number of things, as you will see later in this lecture, that you could have actually usefully done with that. But they quickly decided that that was not going to work out for Java. And the reason is that as simple as the type system of Java looks, it actually has a number of unhappy words. Java has an automatic conversion from these primitive types, int, short, long, and so on, to the wrapper types. And that automatic conversion is responsible for pages and pages of verbiage throughout the Java language specification. Think of overloading resolution. That if you have two methods where, say, one of the parameters is of type int and the other is of type integer, and now you call that with an int, which of them gets called? What if you call it with null, which of them gets called? So there are rules in the language that deal with that situation that are complicated. There are rules that have to do with generic types and type variants that are complicated, as you will see very soon. And so the last thing that the Java designers wanted to do is mess with that type system, because they have had like numerous instances where the type system was kind of weirdly defined in edge cases. The other thing that makes it complicated is the conversion from generic types to raw types, that if you have a list of integer that can be converted to a generic list. So the type system in Java is complicated by its history, and they didn't want to mess with it any further. Scala has the luxury of having started without some of that baggage, so they were able to come up with a better type system early on. But Scala in a way suffers from the same problem right now, that there are other more experimental types that, like I said, we're not really covering, and they are busy restructuring the core of Scala to put those types on a sounder foundation. So let's talk about a couple of type-related concepts. Strong typing. So strong typing means that the compiler and the runtime system together guarantee that no type error can occur in a program. So as an example of strong typing is, look at this Java code. I say code hello code.println. This Java compiler or the Scala compiler will catch this error without trouble, and they will say, we'll just not compile this. Now, not all Java errors are caught at compile time. There are several classes of errors where the Java compiler will let you write code that can potentially throw type errors at runtime. I'll give you an example. Here I have an array of 2 words, and it's typed as a string array. Now I make a variable objects that is typed as an object array. Nothing wrong with that. And now I assign words to objects. That does not make a copy of the array. That simply means I now have 2 references to the same array. Words refers to the array, and so does objects. Now this is legal in Java because string is a subtype of object. A string array is a subtype of an object array, and I can make this conversion. But that conversion is unsound. It can lead to errors at runtime. Move on to the next line. I say object 0 is a new watermelon. Well, that of course compiles because obj0 is an object. A new watermelon is a subtype. Watermelon is a subtype of object, so I can assign from the subtype to the supertype. But this is bad, right? Something must happen at runtime somewhere, because now obj, which is the same array as words, contains a watermelon and a string. Someone could take out words bracket 0 and call whatever to uppercase on it. You can't turn a watermelon into uppercase, right? So something somewhere must now throw a runtime error. Now in Java, the way it works is that this line here will actually yield a runtime error. You get an array store exception if you store a watermelon into an array that was constructed as an array of strings. So the Java designers here made a trade-off. They said, we don't always want compile time typing. Some errors we're willing to have only detected at runtime. Why did they make that decision? Because they felt in general it was so convenient to be able to make the conversion from an array of a subclass to an array of a superclass, that they were willing to allow that conversion even though it's sometimes unsound. Now, we do have a guarantee, though, in Java that all type errors are caught somewhere, either at compile time or at runtime. That's what strong typing means. So Java is strongly typed in that sense. Other languages are not strongly typed. In C and C++, it is possible to write code that contains type errors that are discovered neither at compile time nor at runtime. So here I give a very trivial example. I have an array of 2 integers. I take the starting address of that array and I cast it into a double store. Now clearly that is not a very smart idea, right? Because this is not an array of floating point numbers, but the cast will compile. You'll get a warning. And I could overcome that warning too with a little bit of extra firepower. I could move this first into a void star when I won't get a warning, and then I can cast the void star to a double star, which also won't give me a warning in C. And now I take out the value here. Well, that will compile for sure because values is a pointer to double. But what I get is some bit pattern that the Lord knows what that bit pattern may be. And so manipulating in any way is unsound. And I can do many, many other type errors like that. I could have an error like with objects in the same way by casting from one type of objects to another kind of objects. And you can generate arbitrarily bad behavior in C and C++ that neither the compiler nor the runtime system will catch. That's particularly a problem with dynamic memory allocation. It's very easy in a C or C++ program to corrupt the heap, to overwrite some part of dynamic memory, and then unpredictable things will happen later. Yes?
Doesn't that mean bad actors could also inject code somehow?
Oh, totally, right? And you could easily in a C or C++ program get a hold of some area that contains code and write something into that later then gets interpreted. But that's not something the bad actor thing is not even the biggest problem. The big problem is that it is stunningly unproductive to program in C and C++ because it's usually just a question of time before someone makes such an error and corrupts the runtime data structures. And it's very, very difficult to detect. It used to be that we were teaching C++ to introductory students, and we used a compiler that tried to detect where the memory outside the student area was corrupted. And whenever it found such a corruption, it printed an error message. I've had students coming into my office hours who were surprised that this particular program that they wrote did not produce that error message that every other program that they wrote had produced. So these are exceedingly common mistakes, and they really are very, very hard to detect. If you have a large C or C++ program and it somehow mysteriously corrupts memory, you are in for days or weeks of really bad time of finding out where that happens. Whereas in Java, or the languages that you're generally familiar with, you just get an exception. And those exceptions, are really your friend because they say a type error has occurred and you must fix it. Now, the other dynamic that you have with types is what's called static versus dynamic typing. So static typing says that every type error is caught at compile time. A statically typed programming language will never produce a type error at runtime. There are such languages, but you have not seen one. Java comes fairly close. Java will find most, but not all, errors type errors at compile time. So we've seen the array store exception. That's one that Java has decided to defer to runtime. Java could make an effort to give us types that's the way you can say this variable can never be null. There are many cases when you might want that. They could have had a richer type system that detects where the null pointer exceptions occur. They could do that at compile time. There are languages that do exactly that, where you have nullable versus non-nullable types. You could say this thing contains a string, or it might be null, versus that variable contains a string and it shall never be null. And then the compiler will tell you that if all variables are declared not to contain null, that your program would never ever die with a null pointer exception, which is a nice feature. No one enjoys their program dying with a null pointer exception. In Java, they've decided that tracing the null pointer exception at compile time is too tedious, and they're leaving it to runtime. Now, some languages, on the other hand, are far more dynamic than Java and make little, if any, effort to find errors at compile time. So JavaScript is a very typical example. In JavaScript, I declare a variable without ascribing any type to it, and the compiler makes no effort to track types. So here X is declared as nothing in particular. It holds a string. And it's perfectly legal later to put in something that's not a string but some other object. That, of course, means that when you call a method, that the compiler can never guarantee that this particular call will succeed at runtime. It might, or it might not, depending on what X happens to hold at this particular time. And so this is just the way JavaScript is. It makes it much easier to write the compiler, of course. It also makes it fairly easy for the programmer, who doesn't have to worry about types at all, as long as they work out. Now, what's better? There are people who say dynamic typing is great because the programmer doesn't have to worry about it. And as you'll see in the next several slides, types can get very complicated very quickly and lead to situations where programmers waste time worrying about types when those errors would never actually have any impact. When the compile time type errors are kind of just an artifact of the type system and not something that would ever create problems in programs. On the other hand, other people say that it's very common to make type errors, and if the compiler can catch them, then that's makes programmers more productive than if they're all caught at runtime. Yes?
Do you agree with the notion that dynamic typing languages such as Python are unsuitable for large programs?
So what some people say is that a language such as Python, which is dynamically typed, is inherently less suitable for large programs because all of the typing is implicit. And I mean, the argument that goes for that is that if you now put a new programmer onto a project where they don't see what the expectations of the various contracts are, they are more likely to make these type errors. I've not seen any research that backs this up in practice. And people write very large programs in languages that are eminently unsuitable for them. But it makes intuitive sense that because the types are a part of the contract, that making them explicit is kind of a good idea. So there's research where types, for languages where types are kind of used for documentation only. And but where the compiler then it gives you maybe warnings, but it lets you get away with more things. And where you can have a mixture where you say at the boundaries of your contracts, you're supposed to put in types, but what you do in the inside of a module, that's kind of you're on your own. So, and no one really knows, I think, with any actual research, what the best thing is. The intuitive feeling that a lot of people do have is that probably the more static typing is generally better for things that need to last longer, that have many programmers touch upon them. And in a way, Scala has a good thing going, because Scala gives you the convenience of not having to write down types. So you're going to say val, and the type is inferred. So having a good type inference goes a long way of giving you the benefit of both, where the programmer doesn't have to do a lot of housekeeping, but one still gets the benefit of compile time types. So the rest of this lecture wants to give you some respect for that. Types can be helpful, but types can also be hard and confusing and get in the way of intuitive understanding that programmers have. And so it's a real challenge to come up with type systems that are both flexible and safe. And so we're going to get into that with parameterized types. You all know what a parameterized type is. It's a type that has itself a type parameter. I'll start with a simple example. So here I have a type called pair, and a pair is a thing that takes two elements of type T. So I have a first and a second thing here. And so when you make a pair, then Scala is actually kind of helpful that it figures out, because this is two ints, then it's going to make a pair of int. If you give it two strings, it's going to make a pair of string. So it's a type that itself depends on another type. And it's something that you want all the time, right? We have lists of string, we have array of int, and so on. So we're used to having these parameterized types as something that's a normal part of programming. In fact, when they don't exist, things do get a little painful. Early versions of Java only had generic lists. And then you had to, as soon as you put something in there, you got it out as an object, and you had to remember to cast it back into the correct thing. And it was a big pain. That's why Java 5 gave us generic or parameterized types. So the type parameter for the pair class parameterizes the class. You can also parameterize a function or method. Down here I have a first to function that has a type parameter T. So that means there's any number of first two functions. So this particular function here takes an array of that type T, and it gives you a pair of the first two elements, here, just to do something. So you have parameterized types, you have parameterized functions, and those are kind of natural and normal things that you want in programming. Now, sometimes though, you need to be more prescriptive about those type parameters. So let me give you a simple example. Here I have this min function here. What does min do? Is it takes a pair of a type T, and min has a type parameter T. Then it checks whether the first element is less than the second element, and if so, it gives the first, otherwise it gives the second. This line of code will not compile in Scala. And the reason is simple, that p.first is of type T, right? Because p is a pair of T, and then p.first has type T. p.second is of type T, and the Scala compiler cannot guarantee that the type T has a less than operator. And so the Scala compiler will say, I will not allow you to declare this min function. That's what Scala does. So they've made the decision that you can only define functions when the body of the function would work out for whatever you can plug in for T. C++ made a different decision. In C++, you can perfectly well define such a min, and then when you use it, then the compiler will check whether the particular use is going to work out. So you could use min on an array of, on a pair of ints, but you would not be able to use min on a pair of watermelons. And if you tried the latter, then the compiler would squawk and say, I don't know how to compile the less than on those watermelons. But in Scala, they've made the decision that if you define min like that, then min is a universal thing that works for all t's. Otherwise, you, the programmer, have to explain exactly what t should be. So we can constrain the type t. And here's how we do it. We say that min is only defined for types t that are a subtype of order of t. So the less than colon is the international symbol for subtype. That means t is a subtype of ordered of t. Ordered of t is a trait, which is the same as is a Java interface, or very similar to that, and it produces a less than method for its members. So ordered of t means that t has a less than method. And in that case here, then the less than method will work fine.
Wait, so does that line compile that and instantiate anything?
Yes, so this line here will compile.
Well, what's the point then? Because what...
Well, now if...
Aren't you just going to have to do what C++ does anyway? Because what if you find something that's not in order T? It's going to try to...
Then that will not compile, yes.
So, but you got to do the check still.
Well, so the thing is, it's always a question, when should an error occur? So in the C++ situation, someone will write these templates, and there's kind of an implicit understanding from whatever happens on the right-hand side of the definitions what the rules are for the type. And in C++, people will write these templates, put them in a library, and then someone will later use them, not necessarily fully understanding those requirements because there's no documentation that's implicit. And then the compilation will mysteriously fail. Whereas in Scala, the rules are spelled out right here, right in the code, and there's no question about what the rules for T are.
When C++ compilation will fail and the error messages can be bad sometimes, but they'll say like, there's no add operation.
That's exactly what they will say, yeah.
So, kind of have it right there.
Yeah, I'm not saying one thing is better, one thing is, it says these are the two phenomena that exist. And so Scala is the way that they say the designer of the library is in complete control over what can go in there. And so one disadvantage of the C++ approach is as people put in more methods into a template class, previously compiling code can now fail. Because you could now use an operation that previously, somehow wasn't used, and so all the code just compiled as fine, and now all of a sudden it fails, and so that's never a good thing. Whereas in Scala, that can't really happen. As long as you keep the contract constant, then all the existing code will continue to pass. You had a comment.
Yeah, I was going to real quick question. Does Java have the same thing?
Yes.
Okay.
Yes.
Good enough.
Yes, so in Java, you could, the syntax is a little bit different. You would say,
I used it before. What am I talking about?
yeah, so it's a T extends
That's right, yeah,
comparable, right? Yeah, yeah. So it's
Actually, I think when we had to write our first assignment, I did this, and you told me don't do that.
oh, well.
I just remembered that. Sorry.
But in general, it's a legitimate construct that you see all the time. So yes, so Java has the same kind of type bounds, and yeah. Now, just as a technical aside, we're going to be using this in a lab, and where I would like to be able to have this lead to success. But there is a technical wrinkle with primitive types where one has to go the extra mile with this bound. And that has to do with integers. That in Scala, it wants to be the same thing as a primitive type int in Java, but then in order to do anything with it, it always gets converted to a rich int, and that conversion needs to be allowed for this code to succeed, and I don't really want to go into the mechanics at all, and so you need to use this kind of weirdo operator, the less than %, which means it's a subtype after some possible conversion. This operator is now deprecated in Scala, and there is in fact a cleaner solution to this whole thing that we'll see next Monday, but just for the lab to work out, I'm putting this thing on. So let's not worry about this too much. So really, the type, as you'll also see in the lab, the type ordered is a little bit flawed, but I just wanted to lead in with something that's conceptually simple and that could be made to work better if you didn't have some historical ugliness in here. So the logic here is that it makes sense that to constrain these types so that you can write safe implementations of things that don't work out for everything. Okay, so far we're still not in the danger zone, but we're now approaching. So consider subtyping that comes from inheritance. If student is a subclass of person, then you should be able to take any student object and use it where code expects a person object. In other words, the type student is a subtype of the type person. And now here's a good question. Now let's say I have an array of students, and I have some method that is willing to accept an array of person. Should I be able to pass the array of students to that method that accepts an array of person? Now in Java the answer is yes. So Java allows that conversion from arrays of a subclass to an array of a superclass, and in fact we've just seen that on this slide here, right, where we have an array of strings and we were allowed to convert that to an array of objects. It's unsound, it can lead to runtime errors, and in Java we accept that. That's what the array store exception is for. It means that the Java runtime system instruments all arrays so that those errors are caught at runtime. Scala made a different decision. In Scala they said no. They said, so in Scala, generic types or parameterized types by default are what's called invariant. So if G is a generic type, such as array, and now you have S as a subtype of T, then that doesn't mean that an array of S, or an array of students in this case, is a subtype of array of person. They just say there's no relationship between. Array of students is one type, array of person is another type. You can't convert one to the other, you can't convert the other to the first. That's the decision that the Scala developers made. Say, by default, even though there may be a relationship between this and that parameter type, that doesn't mean that there's a relation between the whole thing here and the whole thing there. Yeah?
So I'm going to guess the reason they did this is because they realized that if you wanted to do that, it's as simple as like a math, or like there's a quick expression you can call if you want to be explicit about it.
Well, it's not that simple, because let's say you have some code that takes an array of person. There is no way in Scala to go from one to the other without shoveling all of the students into a new array. So there really is a cost to this, which is why in Java they allowed the conversion. And then they have a different cost, namely of the runtime check. But in Scala, they do allow some conversions of this kind, namely for lists. So if you have a list of students, you can assign it to a list of person. So if you have a function that takes a list of person, and you happen to have a list of students, you can forward it just fine. Yes?
So then what happens if you try to put a person in the student?
So now what happens if you try to put a person into that list of students?
Yeah.
Why, you can't, because
immutability.
lists are immutable, right?
Yeah.
So if you have an immutable collection, then you're in a much happier situation.
But if it's a var,
Still, the list is still immutable.
Oh.
The var would mean the variable, something different. But
Okay.
if you have an immutable collection, you can't wreck it. You can't store something into it. So the Scala folks said, hey, this is good. Immutable data structures, it's perfectly safe to do the type variance. So the type variance means if this thing here varies from student to person, then we'll say the list of student varies in the same way to the list of person. That's called covariance. Student is a subtype of person, therefore list of student is a subtype of list of person. You indicate that in Scala by putting a little plus in front of the type parameter. The plus means this is a covariant type parameter. So in other words, if one replaces T with a subtype, then the list of the subtype is a subtype of the list of the supertype. You can also have the opposite relationship, where if you vary the type in the other direction, and that's called contravariance, and it's easiest to explain with an example. So there is a interface, or a trait as it's called in Scala, function1, a function with one argument, that takes a type for the parameter type, and then it has a return type. And here's how it's declared in Scala. So it says minus T1 and plus R. And here's what that means. That means that if you vary the parameter type, then the function varies in the opposite direction. So let's try that out. So we're going to vary the function type, the parameter type, so that here it's person and here it's student. Now notice that student is a subtype of person. Right, so we would write student less colon person, or person greater colon student. But now when we put it into the function 1, then we have here the variance in the other direction. So person is greater than students, more encompassing than student, but we now say a function person is less equal function student. So what does that mean? That means suppose that you have some kind of a process that is willing to do something if you give it a function 1 student comma string. If you give it a function that consumes students and produces strings. So you have that process that says, I'll do whatever I do if you give me that function. Now you happen to have a function that can turn any person into a string, say by just printing its name. And now you give that function to your process. And this assertion means this will work. Function of person string is a subtype of function 1 student string, and actually it's perfectly safe, right? Because what's that process going to do? It's going to take the student consuming function and run it on only students. Now you're giving it a person consuming function. A person consuming function can perfectly well consume students. Every student is a person, and it turns those to strings. It's entirely and utterly harmless. So this conversion, the subtyping direction is sound, and that's what we express in Scala by saying you have this minus relationship in the first parameter. And if you think about it for a few minutes, you'll see that the plus R is equally justified. So the Scala programmer is told when they define a generic type, a type with a type parameter, they should think through each of the type parameters and see, is it covariant, like you have for the list? Is it contravariant, like you have for the parameter type of a function? Or is it invariant, like you have for a mutable array? And then you should put a plus or a minus or nothing in front of the T. So that's how variance is done in Scala. And it's overall, it's not a super difficult concept. You just have to get used to the fact that when a programmer designs a generic type, they should think about, how is it going to be used? Are people using it with inheritance? And if so, what should be the subtyping relationship on the result? So I'll give a concrete example here with an immutable list that is the most primitive list implementation that you can think of. So I have a generic list here that takes a covariant T. We can have a head and a tail of this list, and then I have an empty or non-empty subclass. You've seen that before. And so I don't even put in any convenience things with colon in here. Notice that there's no mutation, of course. All I can do is take the head and take the tail, or construct with this constructor. So now let's see what happens if we mess with this list here. So over here, I'm making a list of strings, a G list of strings, by starting out with an empty list of strings, and I'm being super explicit here, right? An empty list of strings, and I add a foo in front. That's now my list of strings. Here it is. Now I take that list of strings and I add a 1 in front of it. And that's perfectly fine. I have not wrecked what foo is. Foo is still the same list containing the string foo. And bar now contains the number 1 and the string foo. And Scala correctly says that's now a list of any. That's the common supertype between integers and strings. Okay? So it's type safe, and Scala just honestly reports what's the best type that it can ascribe to this. Okay? So it's a list. It has a type. You can do things with it, maybe not very much, because when you take things out, you don't know very much about them. But it certainly is completely safe. Now, unfortunately, things are more complicated than that. So I'm going to give you a pitfall that can happen with variance that shows that life is just not as easy to say that covariance just means don't mutate. So even if you have completely immutable situation, covariance can still give you surprising issues. So look at this definition here. I make now a stack of double. Stack is operations push and pop like normal. And let's say it's an immutable stack. I can make an immutable stack where push makes a new stack. But then I still can make myself a bad situation. And really the culprit is, again, inheritance. Inheritance is really difficult for type systems to swallow. It's, of course, something that you often want, but it can create all sorts of headaches, and here is the bad stack headache. So let's look at this class here, the bad stack class, and see what it does. It extends stack of double. Not stack of all t's, but just stack of double. It overrides the method of stack of double. That's what inheritance is all about. You form a subclass, you override methods. It overrides the push method. That push method takes a double. And now what the bad stack does is it calls super.push. When it only pushes the square root, it's bad. Okay? So that's what a bad stack does. And a bad stack is a subtype of stack of double. Why? Because that's how inheritance works. You extend the class, and that means it now becomes a subtype of the original class. When student extends person, student becomes a subtype of person. Now, stack was a covariant collection, an immutable covariant collection. And so stack of double would be a subtype of stack of any ref, because that's what it means to be covariant. Double is a subtype of any ref. So the stack of double is a subtype of stack of any ref. But this is going to get us into trouble, because if bad stack is a subtype of stack of double, and stack of double is a subtype of stack of any ref, subtype is transitive, so that means that bad stack is a stack of any ref. So that means if I have a bad stack in my hands, I can assign it to a variable that is typed as stack of any ref. Now, when I have a variable that is a stack of any ref, then no one can stop me from pushing yikes on it. Right? Yikes is an any ref, and I can push a yikes onto a stack of any ref. But what's that going to do? Bad is a reference to what? It's a reference to a bad stack. So now, yikes becomes E. So now I'm going to take the square root of yikes. Now remember, this whole thing is supposed to be compile time type safe. It must be so that anything that compiles runs without an error. So somewhere our logic must have been flawed. So either we must give up on the fact that extends yields a subtyping relationship, or we need to give up on the fact that a stack that is immutable is automatically and safely covariant. And so it's the latter that we're going to relax on. So when we try to write stack like this, where we put in a pop and we put in a push, where the pop yields the new stack without that last element and the push yields a new stack with that last element. At this point, the compiler is going to say, I will not allow this to happen, because this plus here says it's covariant, but it's going to say this parameter t is in a contravariant position. So they cooked up a set of rules that say that a covariant type cannot occur in certain positions. If it occurs in this position here, then the designers of Scala realized that that conflicts with method overloading or overriding, with method overriding. And so that is disallowed. So the compiler will say, hey, I'm not allowing this plus because this t appears in a contravariant position. And then it applies co and contravariance for more complicated cases that we're not going to get into. But that's what it does. So it actually can be a little hard to write a generic class where the compiler lets you get away with this plus here. Yes?
I'm not really understanding. You're saying that what if you don't call anything on, a subtype of T?
Well, again, so the truth here kind of have the same constraint that what if you don't? So in the world of Scala,
Why not just complain if you try to call it?
okay, in the world of Scala, there is no what if you don't. In the world of Scala, it is that if you set out a description that has class stack of plus t,
Right.
that means it'll always work. It'll not just sometimes give you an error or not. That means that at this point, you can instantiate a stack of anything.
Oh, okay.
There'll never be an issue with this.
Oh, okay.
So it's a very strong guarantee.
Understanding. Maybe you're telling me that it allows you now to use that T parameter?
No. Well, here's what Scala says. Scala says, I'm not allowing this plus because over here the T is in a contravariant position.
I see.
So that means you can form a stack of T. Scala is fine with that.
Oh, okay.
But if you say stack of plus T,
What makes that position there contravariant?
okay, since you asked.
Yeah.
So a position is contravariant if it is a parameter type.
Right.
Or if the parameter is a function and it's a return type of that function.
Okay.
And the parameter is covariant if it is a return type, or if it's the parameter type of a function parameter. And then there's a recursive set of rules that deals with functions that accept functions.
I just don't understand what makes that contravariant.
But because they say that if it's a parameter type, they say it's contravariant. So Professor Odersky says that's the rule. Return type covariant, parameter type contravariant, and then if the parameter is itself a function, then it flips inside that.
I thought code and contravariant referred to like enumerable sets.
No, that's just the name that they gave it. I mean, they could call it, up and down or whatever.
Really? I thought
There's no intrinsic meaning to co and contravariant. It's whatever we want it to be. So for a position of a type,
Okay, so it's I've seen the terms covariant, contravariant used to describe like iterating over sets, like the arrays you were describing.
All right, so we have used the term co and contravariant before.
So this is a different kind of cone.
Kind of. Okay, let's go through this
Maybe that's
slowly.
why.
So we have said that a covariant type parameter.
Right.
That means that if you have a variance in the type parameter such as this, then you have the same variance on the generic type. That's a covariant type parameter. Over here, we're having a contravariant position.
Oh.
So a contravariant position of a type parameter
Yeah,
says
okay.
where that type parameter occurs in a particular declaration.
But isn't that in order to enforce? Isn't that in order to enforce the types?
Well, like it's tried to say up here, even though you have what seems to be like a safe situation, you have a immutable stack where you don't think that you're going to get into any variance problems. You can get into variance problems in other ways by using subclasses. And the thing that gets you in trouble is that over here you have this type that conflicts with the type here. And one way of excluding this trouble, which would require some amount of proof and thinking this really through, but the Scala people did that. One way of excluding that trouble is to simply disallow the T to occur in this position.
Okay.
Now, I didn't prove that, right? But I could, given enough time.
That's probably something.
Yeah. So it's very good that you asked, because this is complex and subtle. So they figured this out and said that if you disallow these kinds of things, you can't get yourself into the trouble that I've shown before.
Okay. So there's some proof.
There's some proof somewhere that we could reproduce it. So it's a little bit more subtle than just putting it into a plus. You also have to make sure that your type parameter doesn't occur in the wrong places. Now that sounds like kind of poisonous, and it turns out in this particular case, you can rewrite push in a way that gets you out of trouble.
Wow.
So you can rewrite push like this, that you say that push takes a type parameter n, that's for the new value, and then it returns a stack of n, and now it'll all compile happily, because notice that this thing is not t.
Oh, I think I understand.
It's n, right?
So
So
you have to apply the constraint on the methods type parameter
Yes.
as well as the class type.
right. So then you have to
Okay,
rewrite.
now I totally. Okay, now never mind. I totally understand. What you're saying.
So now you have to rewrite
I
the
was
method.
misreading it. I think.
So you have to rewrite the method like that, and you, as the implementer of a Scala class, would really
You
have
know what
to.
I thought it was? I thought that when you declared the class type parameter, it was binding that plus to that t and passing it to the. I was like, what?
No, I mean this
It's not, because it's a different. Yeah, I
this
understand.
plus is not bound to the t. It says something about
Never mind.
if t varies, how does the whole thing vary?
No, I got it.
So we have to rewrite this thing here in this way, and I'm not going to go into the gory details because we're not going to do this. This seems kind of like a weird trick, but it does actually work, and now you can no longer do that override thing in the bad stack. So if someone were now to try to form bad stack, it wouldn't work because they would have to explain how to do bad stack for any supertype and not just for the double. So you can't just apply the square root anymore. So I don't want to get into all of the gory details here because it's going to make everyone's head explode. What we learned from that is that type parameters are difficult. And that's just so what about Java? That poster child of a blue-collar, simple programming language where nothing hard ever happens. Well, Java has generic types. You've seen list of t, comparator of t. In 151, you probably learned how to write these things. In Java, is there any relationship between the list of person and the list of student? No. In Java, types are invariant. So you can't move from one to the other. Well, but oftentimes you kind of want to do that, right? So Java has an entirely different solution for doing variants. You can't declare variants as a global feature of a generic class, but you can do it on a case-by-case basis. So here I have an add method that has a list of people, and then it wants to add more people to it, and I'm now declaring this as a list of question mark extends person. So that means it's a list of anything that is a subtype of person. You know, a list of students would be fine, or whatever. And that makes sense, right? You can add a list of students to a list of people. It's safe to do. So conversely, you can have the variance in the other direction. Here I have a list of people, and I want to compare the people and sort them with that comparator. Well, if the comparator compares people, then of course it can rearrange the list. What if the comparator compares objects? Say, sorts them by the hash code or something silly. Then that's fair, right? It can surely compare the people if it can compare any objects. And by using the variance in this direction, then that is safe. So here, little question mark extends and question mark super. You've probably had a lecture in CS 151 that went through that. And if you poll 1,000 Java programmers, you will find that 999 of them have interesting and bizarre understandings of what question mark extends and question mark super actually do, and can't use it properly because it is confusing. But anyway, this trade-off was made because in 2004 there were no immutable collections in Java, and so they said, okay, this use side variance, the syntax may be a little icky, but it doesn't happen all that often. Most programmers will be able to live a happy life without really worrying about this stuff. In the collections, yeah, we have to worry about it a little bit. And it was considered a good trade-off, and one didn't have to go through the full bore variance that you have in languages such as Scala. In 2014, that decision no longer looks so hard. So in 2014, Java 8 got a type or interface called function T. That is a function that it's actually function TR. Sorry about that. So it's a function that takes it that consumes T's and returns R's. And that interface then has an and-then method and a bunch of other methods that composes two functions. You first do one function and then the other. Now you compose a function that eats a T and produces an R, what can you compose it with? Well, the first one produces an R, so the second one has to consume an R. And then it produces a V, and that's the end result. Except this function, well, it must consume an R, but if it consumes a superclass of R, that's fine too. And if it produces a subtype of V, that's fine too. And so you have to express this variance in every single method that uses functions. And so when you look at Java 8, just about everything that takes, say, a predicate or a function, it always says question mark super in the parameter, it always says question mark extends in the return type. There are now hundreds of definitions that consume these kinds of functions, predicates, suppliers, consumers, what have you, all over the standard library. And they all have to be uglified by question mark super and question mark extends. In Scala, you have a single minus and a single plus, and you never have to worry about any of the stuff because all of the variance is now automatically declared, and you can just say here the natural types, and the compiler does the rest. So that's the way it is. They're not going to retrofit Java for this very likely, but in C# you have both. You can have both the declaration side variance and use side variance. So the upshot of this is that you have something that's very, very simple. You have generic type, a type constructor. You have some types, and you want to say a list of that type, a map of one type to the other type. And then you also have subtyping because of inheritance. A person is a subtype, student is a subtype of person. And then you want to somehow control what that means for these collections. And however way you do it, it gets complicated really quickly. So that is the rabbit hole of types that things that superficially seem very simple interact poorly with each other, and then programmers have to worry a lot about type declarations. And that really is where the Python people say, hey, we don't worry about any of this stuff. You know, conversion from a list of person to a list of whatever, we don't even declare them as lists. We'll just use them in the right way. In 99% of the cases, nothing bad ever happens. So that is why the Python people say, you know, this is not such an unreasonable thing. It's not that the simple types, you know, are a burden. It's that the interacting complicated types, they are a burden. So I guess I talked so much that we don't have really time for this lab. So how about I just demo this? It's not quite the same, but that way we'll have a recording of it, and then you can still do this on your own if and when you feel like it. So here I'm going to start with two classes, person and student, the same person and student that we've always looked at. And now I'm supposed to demonstrate that student is a subtype of person. So let's get rid of all of this stuff here. So I'm just trying to clean this up. Okay, so I've commented out the stuff that we need later. So I'm supposed to show that student is a subtype of person. And so the easiest way to do that is I make myself a variable P that I declare this must be a person. That's how you do it in Scala. And now I assign a student to it. Who's a student? Diana. And this works. I get no squiggly errors. Whereas if I do the opposite, if I try to make Harry into a student, then I get an X here that says it's not. Okay, so that's an easy way of testing whether one thing is a subtype of another. You just explicitly declare the type, and you see if you can do the assignment. Yeah.
So when I try to print it out, the P is give me a student and a person. Can I try to bring line?
Okay. Okay, it's not printing, but what is it printing for you?
It's printing the name in the ID.
Of Diana?
Yes.
Of course, because what does it mean to say this is a reference to Diana, and P is another reference to the same thing?
Yeah, but it's not the ID which is not
Well, P is a reference to what we know for sure to be a person, but it might be a subtype of person. That's how references work in Java as well. When you have a reference to an object, you know that it's for sure the declared type, but it could be a subtype.
It's like if you print out a person in Java and that person happens to be a student, it's going to call the toString method of the student.
Yeah.
So it's going to return probably extra.
Yeah. No. So you have to distinguish between the type of the variable and the type of the object to which the variable refers. All right. Add line of code to demonstrate that an array of student cannot be converted to an array of person. Well, let's make one. So I make an array of students. Students is array of Diana Frank. Let's make sure this is an array of students. I mouse over it and it says array of student. Okay. I make an array of person variable, and I try to assign students to it, and that doesn't work because it says type mismatch, found array of student, required array of person. Okay, so it doesn't work. What happens if you try list instead of array? So I'll make this one to a list, and this one into a list. And now students is a list of student, and now this works fine. Why? What's that?
Can you repeat that question?
Yeah, why?
Well, like,
So, why is it that this works? Why can I assign a list of student to a list of person, even though it didn't work for arrays?
Because lists are
you decide some type of the person.
Lists are covariant. So, when I look at list, here is good old list.
Yeah, I know what you mean.
Here it says list of plus A. So it's covariant in its type. Okay? That's why it works for lists. Okay. Now it says, what happens if I try to add a person to a list of students? Does it work? So I have here a list of students, and now I take students, and how do you add a person? I don't know, Harry. Well, that doesn't work. Why not? Well, it doesn't. Yeah, it's a val, right? It's immutable, and so none of this would work. So can I put one in? I guess I could use cons, right?
You have to assign it. You have to do that.
Okay, so then val something. Okay. That seems to work, and let's see what something is. It's a list of person. Okay, it's perfectly legal. But now something has at least one person in it, plus a bunch of students. So the type inference works exactly as we would like it to. It gives us the accurate type for this.
Is that the contravariant?
No, nothing to do with variance. It simply has to do with the fact that, well, let's look at we could look at the definition of cons. So it says that cons will give us a list of A, and now it needs to unify this thing. This is a list of something. This is a something, and it says, okay, I'm going to convert students to a list of person, because then I can apply. This is covariance, not contravariance. So it converts students to a list of person, so that it can cons together with this person. Okay. So next question. Now we're making this pair class here, the my pair class. I have to call it my pair because there is a pair installment. So here's my pair, and the now it says, is a my pair a subtype of student, subtype of my pair of person? Okay, let's make it some my pairs here. So this would be my pair. This is a my pair. This you have to take out. And now it says, not on my pair. Oh, I need to undo what I did in the previous class. So now it says type mismatch. I found my pair of students. Required my pair of person. Note, student is a subtype of person, but class my pair is invariant in type T. You may wish to define T as plus T instead. Isn't that a great error message? Right? This message actually tells you how to fix something. All messages should be like this, right? So,
You should look at Rust if you like error messages.
so here, now it works, right? So now I have defined it as covariant, and now my conversion works the way that I want it to work. Okay, excellent. Now it says to add this sum method, and so this method here, sum, takes a function from T to int, where T is the type of the things in here, and then it applies it to the first one, that's an int, applies it to the second one, that's an int, and it forms the sum of the two. And it says, now do this stuff here. We have these two functions. Oh, I can't use P here. Let me take this one out here. And it all works fine. Okay, whatever. So it says, can I call p dot sum of f? Let's find out if we can. Apparently. Can I call p dot sum of g? Apparently. And so it says, it's not surprising that p dot sum of f works. Okay, f is a function from student, and what is p? P is a pair of student. Okay, and the function here, if I have a t here, which is student, then I have a t here, which is student. But why does p of sum of g work? It seems like it shouldn't work because g has person here and not student. And so again, p has t equals student over here, so it seems like this t should also be student. But that's where the contravariance of function 1 comes in, that if you have something that expects a student eating function and you give it now a person eating function, then that works fine. A person eating function can also eat students. So you automatically get the correct behavior in Scala, which is nice. Okay, if you need to bail, go for it, but I'm just going to do the rest and record it. So now it says we should add this max method over here. And so now, as was already on the slides, now we get a hiccup here with a less than. So to fix that, we have to say that we want to be a subtype of ordered. And now the error will go away. Now let's just try that and say, can we do a my pair of 1729 and call max. Now we're going to get a nasty error message about int and ordered, and we're going to fix that by changing this thing to a %. And then the error message goes away here. This is kind of this historical thing that I was talking about. But now we're getting other nasty messages. I can no longer form a my pair of Diana and Frank. And I can no longer form a my pair, in fact, of people. So let me do the... Yeah, so let's... That has nothing to do with the % thing, because even if I undid this again to less than colon, I would still get the same problem. It has to do with the fact that people are not ordered. So I am going to define person now to say it is ordered. To say ordered of what? So I guess it's ordered of person. And now I'm going to override. It turns out that for ordered, let me just quickly look at ordered. For ordered, you need to define a compare method. Very much like with comparator or comparable in Java, right? And so I'm defining the method here. I'm just going to compare the names. And now that didn't seem to help me. Well, let's actually make a different list of people here. Harry and Sally. Oh, not Harry. Yeah, Harry and Sally are people. So what's our problem? Person required T. Ugh. Let's see. I must still have. Oh, because I put a colon here and not extends. I must have done too much C++. Okay, and now I can form the pair of people, but I can't form the pair of students.
Doesn't students need to also?
Because student extends ordered of person and not ordered of student.
Oh.
And ordered is invariant. And so this is why you just weep and say, we want to do something completely reasonable, and the type system is not letting us do it. There's no rescue here. The type system is blocking us from doing something that is very reasonable. What they should have done is they should have made ordered contravariant. And there's some reason why they couldn't do that that has to do with compatibility with Java. And so eventually they decided that ordered is a dead end, and we'll see on Monday the more modern approach that makes this one a little bit better. But what it does show is that a type system can get to be so rigid that it stops you. You want to do so many things, and at some point you can't, because there's only so many rules that you can fulfill at any one time. So that's the moral, that type systems are great because they will prevent you from doing stupid things at compile time. But it can be difficult to encode the real world in type systems as well. So on Monday, we'll learn more about what Scala can do with types that you could never do in Java. So we'll see a more positive and beneficial story. So do your homework, preferably starting today if you haven't started yet, and put lots of questions on Piazza. Thank you.